Hi, I'm Rich with Inside HPC. We're here at PASC 17 in Lugano, and I'm here with Christoph. Christoph, I understand that you're a climatologist. What brought you to this conference?
Well, my group is active in high-resolution climate modeling, and so this is a field that has developed from using vector computers a couple of decades ago, and now we are using much more sophisticated computers, and we have to learn more about how to using these computers and collaborate with the computer science community.
Okay. Have you found, was it a good conference for you? Did you make some good connections there?
Yes, I think there were a couple of really interesting presentations in our field, but also it's a good spot also to look beyond one's own field, to look into other areas that maybe in some areas they are behind and in others they are ahead with some of the ideas.
Well, I'm curious, I used to work at Cray Research back in the 80s, so you mentioned vectors. Is your code still vectorized? If a new machine appeared, would that interest you?
I think it's a good question. Actually, so our code, it's not because the code is vectorized. The problem is suitable for vectorizable computers. So if a big vector computer would show up, all the climate community would use it. But now we have worked 10 years or so to use MPP systems and of course now also the heterogeneous architectures. And that's really a challenge. And I think we made some progress in the last decade, and that's good to know.
And how well does that code scale? Is it? 10 years. There's a grand challenge type of problem, isn't it? Yeah.
So I think that it really depends what methods one uses, and for some of it will be the graveyard for some of the numerical methods, because they will not come up with a good scaling. But for some other methods, the weak scaling is very nice. So if one has something that you can run at high resolution over Europe, let's say, you can blow it up to global scales.
And when we talk about climate prediction and things like that, are we talking like 50 years, 100 years in the future, or even farther?
So today, most of the simulations are done for 100 years into the future, the end of the century.
Yes.
But of course, one thinks about longer term. There is a large set of simulations that takes 300 years already. And so basically the ability to predict on that time scale is really the delayed response of our climate system. So it actually responds to some extent to what is in the atmosphere now.
And in your work, what is a practical turnaround time for that kind of job, for it to be practical?
So I think the turnaround time should be not slower than 3 to 6 months. So we have simulations that take, in practice, that kind of period.
Yeah.
And the time scale comes from actually the fact that PhD students work on it, and we would like to get their work within a PhD, and of course they have to do a few simulations.
So you want to finish the simulation before they graduate and go off, and then you got to start over?
Yeah. So we are basically trying to have codes where you can do maybe half a simulation year in a day or something like that. And then one can do a decade-long simulation.
Well, just to wrap up here, PASC 18 is in Basel next year. Do you think you'll be going to that?
Most likely. I haven't written down the dates, but it's maybe good you remind me about it.
Oh, yeah. So it's July 4th through the 7th of 2018.
Basel is a great place, I can tell you.
Okay. I'll look forward to it.
Yeah.